Hello. We have chosen for our project to control an epidemic from an economic point of view. We were of course inspired by the current COVID-19 crisis. First, we tell you about the general model, followed by a brief explanation of our optimization process, and at last go over our results. Our model is based on the spread of a virus in a city that is connected to multiple other cities. The amount of interaction between the cities is characterized by travel rate, which is also related to economic profit by trade. The following measures can be taken to counter the spread of the virus. We assume that a vaccine is developed and distributed in the different populations. The total production of vaccines and distribution between the cities is something we can choose. We also included that a rushed development costs more than a slower one. A second measure is to limit the travel rate between the cities, equivalent to social distancing, but this has also economic consequences due to lower trade. Most epidemic models in literature are based on the SER model, which is shown on the slide. The beta parameter indicates the speed of the spread, which is determined by the probability of infecting a susceptible person and the amount of interaction between the people. The gamma parameter is characterized by the recovery rate of an infected person. At the beginning of the semester, we analyzed a stochastic model, but due to state explosion and limited computational power, we were forced to use the deterministic model for the optimization procedure, on which we will tell you more in detail.
The optimization problem we intend to address is the minimization of the economic impact of an epidemic. The variables that need to be optimized are the number of vaccines per city, the vaccination times, and the percentage travel restriction. Of course, it has to be prevented that the epidemic becomes unacceptably severe, and this forms a primary constraint of the optimization problem. The cost function is considered to be non-convex, meaning that there are multiple local minima. We are, however, interested in finding a global optimum, and as such we need to turn to a global search algorithm. We have chosen the artificial bee colony algorithm to perform the optimization. This population-based stochastic search algorithm mimics the behavior of honeybees in their quest for food sources. The algorithm will try to find the optimal solution by adopting the swarm intelligence that is observed in honeybees. One of the major benefits of this algorithm is its robustness, and this is the main reason why we opted for this algorithm. The artificial bee colony algorithm uses neighborhood searches to generate new candidate optima. These neighborhood searches are governed by a probability distribution that is updated every iteration. This update will increase the probability that neighborhood searches will be focused around the areas that are most likely to contain the global optimum. We found open source code on Yapis implementing the artificial bee colony algorithm in MATLAB. However, numerous alterations to the program were needed. We encountered two major bugs in the program. On multiple occasions, some methods seemed to return not the number values, causing the program to crash. And we also observed that the program didn't always respect the set parameter restrictions. Both of the problems were addressed successfully. Next, we adapted the program so it could also optimize discrete variables next to continuous variables. And finally, we implemented the possibility to provide initial guesses. In this way, it becomes possible to jumpstart the optimization procedure, which may increase the efficiency significantly.
The objective function intends to sketch the economic impact of the epidemic. There was no cost function available in literature, so we had to define the cost function ourselves. It was important to define a cost function which reflects reality. The objective function is a summation of four main economic costs. The first cost is a production cost. The numerator of this cost depends on the amount of vaccinations in each city, and the denominator depends on the vaccination time in each population and the contact rate between the respective city and the city where the factory is located. The healthcare cost depends proportionally on the epidemic size. The epidemic size represents the total amount of individuals who got infected over time till the end of the epidemic. The third cost represents the excess capacity cost. This cost plays an important role if the epidemic rises above the predefined maximal epidemic capacity which the society can manage. The last cost stands for the trade opportunity cost, which depicts the economic loss with respect to the best possible alternative and is determined by the imposed limited travel rate between the populations mutually. To find the ideal weight coefficients, we created a standard situation in order to easily reason which weight coefficient should be adapted. Many attempts were needed to find the weight coefficients in order that the different costs had the same order of magnitude. Furthermore, it was also important that not all the optimal controllable variables coincide with their predefined boundaries. This slide shows the optimal solution for every controllable variable with the respective values of their weight coefficients for a certain situation. The first result, in the situation with 4 cities, proposes to vaccinate the complete first population immediately, while the other results tend to vaccinate less and wait a little longer to suppress the production cost. This results in a larger epidemic size. The results in the situation with 8 cities have clearly a higher epidemic size. The amount of vaccinations in the first population is mostly higher than in the other populations. The travel rate is still high though. So let's move on to the conclusion. The optimal solution depends strongly on how the objective function is weighted. We can conclude that the population where the outbreak started is vaccinated more than the other populations, and the vaccination time for that population is also shorter. Furthermore, the cases we studied proposes rather to control the epidemic by vaccinating than by restricting the travel rate. We have to denote that it is still necessary to improve the cost function and the weight coefficients.